Hi, I want to talk to you today about Newton's theory of gravity. And to do that, we need to jump back and take a look at Newton's laws understanding the behavior of forces, because he used it as the structure for reasoning out his argument for how the force of gravity seems to work in the example of our solar system. And to refresh your memory, the pragmatic interpretation of Newton's laws of force, the first law is really boring, doesn't really apply in most situations because it says if there's no external forces, motion can't change. Well, gravity is an external force. It's external of an object. First law doesn't apply. Now the second law, some folks would bristle to say that the acceleration is the sum of the forces divided by the mass. Really, Newton said the net force is the change in momentum of an object. Well, I want to focus on this first interpretation. And mass, remember, was described as the inertia of an object. And strictly speaking, we should call this the inertial mass of an object. And then pragmatically, I said the way to think about Newton's third law is draw forces as they act on your object of interest. Usually when we use the third law, it's to draw a pretty force picture to figure out how the object in question is going to be accelerating, if it's accelerating at all. This is the case, though, where we need to go back to the more careful definition. Forces are interactions between two massive objects. Each object feels the force equally, but it feels the force in an opposite direction. That is, the actions are themselves reactions stands for. Is that there's one interaction, one force between the two objects, two ways to look at it. Well, let's put 2 and 3 together and think about a universe that's just two masses. So say it's Earth and the Moon, and that's our entire universe. Well, from observation, the Moon appears to be traveling in a circle around Earth. We had that well established in the 17th century. So what we could argue then is if the Moon is in centripetal motion, there should be a force acting on the Moon. And the force acting on the Moon should go like the mass of the Moon times the acceleration of the Moon. Well, Earth is also hanging out here. Earth is also made of stuff. It has a mass. So therefore, there has to be a force on Earth because there's an interaction between the two that we call gravity. So as the Moon is pulled by Earth, Earth is pulled by the Moon. So the force acting on Earth should go like the mass of Earth times any acceleration of Earth. And through very careful astronomy, you can actually see Earth is accelerating because of the Moon. It actually wobbles back and forth, doing a kind of drunk walk in its orbit as it travels around the Sun. So mass has to show up from each of the objects involved. And Newton took a look at acceleration data for all of the known orbiting celestial objects that he had access to, and he noticed that the acceleration fit a 1 over distance squared pattern. So he proposed that the force then, in addition to going like the product of the masses, had to go like 1 over the distance squared. And as best he could determine, that's it. Now, in the units of force that we use, newtons, which we call kilograms times meters over second squared, it's not the same thing as kilograms squared per meter squared. So at the very least, we at least need something to make the units work out correctly. And that something we refer to as the universal gravitational constant. So, as best as Newton could explain, the force of gravity appeared to go like a constant, which our current measured value is 6.674 times 10 to the negative 11 newtons of force times meters squared over kilograms squared times the product of the mass of each object divided by the distance between each object's center squared, acting on a radial line between the two objects that is always attracting. And just one note, strictly speaking here, this is what we call a gravitational mass. I know from the argument that I just made, we referred to the mass as the inertial mass. And it turns out, as best we can determine, the inertial mass and the gravitational mass are the same. Which is actually one of the big open questions of physics that some folks are out there trying to answer. Why is that the case? And is it really the case? Is there ever a scenario where they might have the same size, but might have a different sign? And on that weird note, I want to thank you for watching. And the answer to that lies into some particle physics that we're on the cusp of just being able to do right now. Thanks again for watching.